The problem we're going to talk about today is surface matching, and I would like to place it in kind of a more global context. And first of all, what is surface matching? So surfaces are what we call two-dimensional manifolds as mathematicians, but also can simply intuitively explain as outer shells of solids in the three-dimensional world around us. So there are two-dimensional objects that folded in some interesting shapes. And basically, comparing surfaces is a core element in many scientific fields. And this is by no means an exhaustive list, but just few interesting applications of comparing surfaces. One is related to data mining. So you think you have a database of shapes. You want to do a shape retrieval based on shapes. That's a problem that people are working on. In medical imaging, obviously, many people are comparing surfaces, whether it's internal organs or the cortex surface. Face matching is, again, comparison of surfaces, the surface that describes the faces of people, and you want to kind of be able to recognize people, to be invariant to expressions, and so on. Another application, which is kind of slightly less explored, is related to biology, and that's something I'm going to emphasize on this talk. I apologize to whoever heard this talk before. A lot of it is from last year. So what is the business of paleontology? So they are interested in shapes, and they basically look at shapes of bones, and they kind of understood very early in their evolution that shapes have a lot of biological meaning, not just purely functional. And basically they look at the same shape from different species as they want to extract the maximum information from the shape. In a sense, the kind of meta goal is to extract something like a geometric DNA of a shape and be able to really say something concrete about evolution. To kind of understand a little bit what is the problem in surface comparison when we talk about biological forms, I show you here three of the same bone. It's called the distal radius bone from three related species. There's the gorilla, human, and orangutan. And I render them especially in this direction, so you can see there's kind of a global similarity between them, but locally it's very hard to say something. And basically when biologists now come nowadays to compare those two surfaces, the first kind of notion that comes into mind is to basically reduce the problem to maybe a bunch of numbers or that describe each of the surfaces, and then compare the numbers in some reasonable way. So basically they choose points on the surfaces, measure the distance between them, and maybe compare those distances. However, these methods are kind of problematic because there's a lot of arbitrariness in the process. Someone has to choose those points in a relatively stable way, stable to natural deformations. And it's not clear how many points you should choose, and whether your choice is already kind of dictating the answer, and so on. So this is really a process which is very user-dependent. Yeah? And it's not something. What they like to do is to be more like the DNA colleagues, where they have kind of a way to compare strings without ambiguity. I'll show you an application which is kind of a recent thing that we tried, which there's no other way to solve it except using geometry. So there are two groups of species that lived on Earth, and according to the current theory, it is believed that there has been a 20 million years gap between when this species lived and this species lived. So these, by the way, are teeth of certain primates. So people believe that there is 20 million years gap between them. And my colleague, which actually collects this data, his name is Doug Boyer, he recently found two other fossils. He actually digs in certain spots in the world and finds fossils. And the fact that he digs them in the same place means that whoever owned those teeth belonged to the same era. And he conjectured that one of them belonged to one of the groups and the other belonged to the other. But in order to convince his friends, he has no kind of a precise way to do that except kind of reasoning about the geometry of the stuff. And if you look at it, it's pretty hard to say something decisive about the shapes. And my goal in this talk is to say that we can take this discussion one level further and define something like a geometric common ground on which we can start arguing about. So we can. I'll actually show you that there is a pretty clear answer which belongs to which group. By the way, the group contains more elements. I just chose two representative of each. Okay, so now I'm going to leave biology. I'm going to describe the mathematical machinery that we've used, and at the end of the talk, I'm going to go back to this problem, and I will show you a solution. Okay, I will not say a solution, but let's say one step toward the formalization of this question. So in surface matching, basically one is given two surfaces. So a surface is basically a very general thing. This dog here is a surface. And there are two kind of products that people expect to get when they're matching surfaces. The first product is a correspondence, which can be a map, but not necessarily, as we will see, which basically means that for every point on one surface, we want to get a corresponding point on the other surface, or more than one point. And the second product that people expect is something which is a scalar, which will have the natural kind of structure of a metric, which kind of encapsulate the difference between the two surfaces in one number. This is very useful if you think about that, like a segmentation of shapes and so on. And the first thing that comes into mind when you want to define a metric on the space of surfaces is you have to choose what is your notion of equivalence. So when do you call two surfaces the same? So the most classical way to say that two surfaces are the same is if there is some kind of a group that relate them. So for example, congruence, if they're a rigid motion one of another, we obviously don't want to consider them different, and we want our metric to be 0. The distance between them is 0. A slightly more modern point of view is the Riemannian metric, which basically says, okay, so this surface has an induced Riemannian matrix from its embedding, and basically all the isometric deformation, the deformation that don't change distances on the surface, geodetic distances, are basically all the same appearances of the same object. Now there is really vast amount of works that try to solve the matching problem in very different fields, starting from structural biology through engineering fields, computer vision, computer graphics. And I don't want to go through, and this is also not an exhaustive list, but I want to kind of give the feeling that there is a big gap in algorithm. Either there is algorithms which are more heuristic and provide good results on certain subclass of the problem, but have no guarantees and indeed do poorly on other subclasses, or there are very rigorous type of algorithms, like algorithms that directly discretize notions like Gromov-Hausdorff distance, but then they basically boil down to NP-hard problem when you write it down and you have to do something like finding some global minima based on initial conditions and so on, and it's really hard to find a global minima of those problems. So this gap is basically is something that people try always to narrow down, and basically what I'll try to convince that it can be narrowed down a little bit. I don't know to what extent, but there's definitely things that can be done in the future to make it smaller. So basically there are so from looking at previous work, there are a few basic questions that comes into mind. The first question is a very simple one. So if I'm giving you two surfaces, and I'm just going to ask you a simple question, can you decide quickly if those two surfaces are isometric? Yeah. So obviously, if I would ask you if they are congruent, if there's rigid motion between them, everybody's going to come up with a lot of suggestions. But if I ask you whether they're isometric, is there a simple algorithm? When I say simple, I mean a reasonable time complexity algorithm that can answer these questions. Once we can answer this question, we can go the next step, and the next step said, okay, so we know to figure out when two surfaces are isometric, that's our kind of equivalence relation. Now maybe you can use this idea to define distances between surfaces which have this kernel. But the distances kind of extend to any pair of surfaces that we can compare, not just say yes or no whether they're isometric. And maybe the last question, which is extremely big and definitely contains the first two, but contains much more, is in general, if we take a surface comparison function or some way to measure distances between surfaces, can we say something about its global optimum in a reasonable time? And what I'll try to convince you by the end of the talk, which is not that far away, is that for surface comparison, the structure of the problem often implies that you can say something about the global solution, and we'll get to that. So the main kind of tool that we're going to use is the notion of conformal geometry, and I'll give kind of a quick introduction to that. So conformal maps are maps that are preserving angles. Here's just a kind of visualization of a map defined on this square. Basically, mathematically, we can ask that the differential is the similarity. Writing down in coordinates, it's basically the Cauchy-Riemann equations. More generally, conformal maps can be defined between two-dimensional domains not embedded in the plane. That is differentiable surfaces. And the definition is basically the same thing. We just ask that the differential of the map, which is defined between those two tangent planes at every point, is a similarity. And we have a definition of conformal maps between surfaces. Now, our goal will be to compute conformal maps between surfaces and use them for something. So the first part of the talk, I'm gonna quickly say how do we compute conformal maps between surfaces. So for certain surfaces, everything is known. So for example, if we talk about the unit sphere, the entire group of bijective conformal maps that take the sphere to itself is the well-known Mobius group. And if we parameterize the sphere with the extended plane using this famous stereographic projection, then we have a very nice formula which we all kind of seen before, which is the fractional linear transformation of the Mobius group. Another canonical surface is the unit disk, and the set of all bijective conformal mappings, self-conformal mappings of the disk to itself, are a subgroup of the general Mobius group, and it can be parameterized in this way. The really important thing which we're actually going to build on in all this thing is the fact that the dimensionality of those groups is relatively small in comparison to all diffeomorphisms. And we know, for example, that to set a Mobius group on the sphere-type surfaces, we need 6 real degrees of freedom or 3 complex degrees of freedom. And for this type surface, we need 3 real degrees of freedom, which is basically, we know that also from Riemann mapping theorem of simply connected surfaces, planar domains. OK, so what do we need to do in order to compute all the conformal maps, or be able to compute all the conformal maps between two general surfaces? So we have these two surfaces. These are, again, teeth, and these are homomorphic to disks. So the component that we're missing is the uniformization theorem, which is basically a celebrated theorem that says that if we have a simply connected surface, let's say homomorphic to disk, then we can map it globally, bijectively, and conformally to the disk. Once we've done that, we basically now can explore all the conformal maps between the surfaces by exploring Mobius transformation from the disk to itself. So for example, here I just pick one Mobius transformation between the disks, and I compose them with the uniformization in this way. And basically, I'm showing you now the conformal map that this Mobius element represents. So you can appreciate that it's conformal because the grid is orthogonal here and orthogonal there. Okay, I mean that the intersection is always 90 degrees. So it means that the angles are preserved. It's not a proof, but it gives the feeling.
What is the complexity of doing uniformization?
So it's basically approximating an elliptic partial differential equation, finite element, linear. But I have a slide about that. We can talk about it later. Let's say that for this thing, you do it once, and then once you do it, there is a closed form formula for the Mobius transformations, and you can basically explore them in an efficient way.
And you are all the time speaking about if they are isometric or what about if they are not isometric?
I didn't say anything about a metric so far, just conformal mappings, something more general. I didn't say anything about metric. Now I'm going to say something about metric. So the first problem we're going to ask is whether two surfaces are isometric. Okay, so we want to answer that quickly. I want to say that conformal maps can help us to do it very quickly. And the reason is kind of obvious. Let me explain. So what do we mean again by isometry? Let me remind quickly. So we have a surface. We basically want to define a metric on it. And we define a metric by taking 2 points on the surface and defining their distance, the geodesic distance, to be the length of the shortest curve that lies on the surface between the 2 points. This kind of makes this a metric space, which we can call a Riemannian metric. We call two surfaces isometric if there is a map between them which preserve all those pairwise distances. So that's isometry. And now, given two surfaces, how do we decide if they are isometric? So the really simple observation here is that isometry is in particular a bijective conformal map. One way to see it from the way I defined isometry is that if we take a very small geodesic triangles, they behave very similar to Euclidean triangles, and we all know from high school that setting 3 lengths of a triangle also makes the triangles congruent, right? So the angles are also preserved. So that would mean, if we take this infinitesimal point of view, that isometry is a conformal map. So what? So it means that if there's an isometry, it lies in a very small space relatively to all possible diffeomorphism. It lies in the conformal group, which we only said has 6 or 3 degrees of freedom. So it's only enough to look in that space. And we also have an efficient way to search that space. So here's an algorithm for finding isometry. We take a surface, we map it through numerical approximation to the disk conformally. We take another surface, we do the same thing. by the way, what is this landscape here? When we map something conformally, we preserved angles perfectly, but obviously we didn't preserve the scaling, right? We cannot, this is not a flat metric. We cannot flatten it without an arrow. So the uniformization said we can make sure that angles are preserved, but the scales will be significant. So here, basically now it's, we can save a positive scalar function which defines how much scale happens. So we can imagine that this peak, it kind of correlates to places with high Gaussian curvature. Yeah? So basically the simple observation says that if those two isometrics, there's a Mobius transformations that takes this landscape, I would call it a density. That's the conformal factors, by the way. Take this conformal density to this conformal density. So we can just, if you want, random Mobius transformation and see if we can get from this image to that image. That would mean that the two surfaces are isometric. Here's an experiment. So here's the two surfaces. These are the approximation that we do for uniformization. I don't want to talk too much about the actual way how we do it. All I want to say is that we can kind of expect that these two surfaces are near isometric. Why? Because when cat moves, we can expect that its skin doesn't stretch too much, which means that the distances intrinsic to the cat do not stretch too much. That's a vague argument, but it means that if we take now 3 points again, that's exactly 6 degrees of freedom of the Mobius transformation. If we take 3 points which are kind of corresponding, and we align those 3 points in the uniformization space, by aligning them by a Mobius transformation, we can expect that if we took points from an isometry or near isometry, then everything else would rearrange, and we kind of extrapolate we reconstruct this isometry everywhere. So let's do that. So I'm just going to apply a Mobius transformation here, and what you see happen is that those black spots here arrange similarly to the black spots here. These black spots basically correspond to the different limbs of the cat. So the leg, hand. So this is probably the front leg. This is maybe the head. I don't know, the head, the leg, and this is the tail. So you see that the image looks very similar. So it kind of gives the sense that you can think about polynomial algorithm in complexity of n to the cube in the number of points to find isometries if they exist. So that's the first proof of concept, and now we can move to the real problem of how to define an isometry invariant distances between general surfaces, not just isometric ones, or near isometric ones, which are also efficient. So the point of view is, like in Euclidean geometry, when you represent quantities, we always like to represent them in a way which is a rigid motion invariant. Why? Because we don't want to bother ourselves with things we don't care about. So we don't care about orientation of stuff, so let's represent it in an invariant way. The same thing, the same kind of concept should apply also to other geometries. So if we have a surface, the last thing that we want to do is remember the surface in coordinates, right? So the former discussion kind of gives a natural way to represent a surface, which is basically an orbit of the conformal densities up to a Mobius transformation. So this is kind of an object. I'm not suggesting to keep that in a computer, yeah, but that's conceptually a good thing to think about. Why? So here's a good reason. Let's say that we want to define a metric between surfaces, and we have a good metric between measures or between densities, and that we all know that there are many good measures, metrics between measures. Let's say probability measures. Then there is a canonical way to connect whatever we got there to surfaces. And how do we do that? We take some metric between probability measures, and then we basically just do a metric quotienting. So we place here the orbits of the conformal factors up to the Mobius group. And we automatically would get a metric between surfaces. So basically this kind of a simple idea connects between general metrics on measures to metrics on surfaces. And the question now is what kind of metric to use. A choice of metric which is favorable for this problem is what is called the Wasserstein metric. And the Wasserstein metric is basically a kind of a metric between distribution or probability measures, which has kind of a physical intuition. Basically, it says that it basically looks at things of the two densities as a pile of dirt, or a pile of some material of mass 1, and you want to rearrange this to be in this configuration, and you want to do it as efficient as you can. So what does mean as efficient? It means that whatever you move, this is the distance, you multiply by how much you move, that's kind of a cost that takes you from this to there. And obviously, there are many ways to rearrange. Basically, how many ways are there to rearrange these two probability measures? Basically, you can look at all measures on the product space which have a marginal of this density on the left and this density on the right. And this, we can call, this is a huge space, right? And we want to choose over this space the one which does the best. So we use this concept for generalization. and you get an algorithm to define distance between surfaces. Then the bottom line is that it's a convex algorithm because this thing boils down to linear programming. I'm not going to get too much to details because I want to talk about the third part on the biological applications. So I'm going to say whatever I said so far in different words now with just images. So what did we do? How did we define distances on surfaces? So we had this huge space of area preserving by measures. It means that measures on the product space of the two surfaces with the marginals. And what we did is looked for a minimum on the space up to some functional. So this is a huge space. However, luckily, when you discretize it, you're spreading some points on the surfaces and so on, this space becomes a convex polytope, right? That's basically those linear programming constraints. We want the sum of the matrix to equal one density, and the rows, sorry, the columns would sum to the second density, and the rows would sum up to the first density, and we get a very nice convex polytope, and we can optimize it in polynomial time. And then what you do with it, we said basically now if you want to use that framework to define distances between surfaces, then all we did is basically said a distance between surfaces is basically a distance between the conformal group between those two surfaces and the area preserving by measure of the two surfaces. That's basically the same way to say it, because what we did is apply the Mobius transformation on a density and ask what is the mass transportation distance between them, what is the Wasserstein distance between them. And you can imagine that if we had the Mobius transformation, which is area preserving, that is an isometry, then we would have a perfect area preserving, and these two would intersect. So in a sense, the distance that we're measuring is the distance between the conformal group and the area preserving by measures. Now the problem with that is that biologists don't like by measures, and the reason is that by measures are not necessarily maps. So they can take a piece of mass here and distribute it to several points on the other. So a certain point here would correspond to many points on the other surface. That's not unlikely, right? Right? But so many people, so for many applications, it's important that you produce map at the end of the day. So in a sense, in order to produce map, all you have to do is something that may seem simple, is to change this with whatever you want to preserve. So instead of area preserving by measures, we can take area preserving diffeomorphisms. Yeah? So smooth maps that preserve area. And actually, we get even a smaller space. The problem is that this space is much less nice than the by measures, right? Because it's nonlinear, and we know how to flow in it with divergence-free vector fields, but we don't in any way know how to optimize globally over this space. This is a huge, formally it's infinite dimensional manifold. It even took a non-trivial amount of mathematical analysis to prove that it's not empty, although people understand that it's infinite dimensional, right? That's a famous paper by Moser a few years back. So in this setting, we have an area preserving diffeomorphism with some function over it, and we want to globally optimize it. So how can we achieve that? So obviously, in the general setting, when the function we don't assume anything on the functional, we cannot really say anything. However, in our problem, where we're comparing surfaces, there is a very strong kind of another assumption on the functional that we use. We use the fact that if the distance between two surfaces is 0, the two surfaces are isometric or congruent, depending on what choice of equivalence we made. And that's something we're actually going to use. So here's how we're going to use it. In case the two surfaces are isometric, the image looks like this. The group of area-preserving diffeomorphism between the surfaces and the conformal map actually intersect. Why? Because we know there is an element, which is the isometry, which belongs both to angle-preserving, conformal maps, and to area-preserving, right? So that's the definition of isometry. So if we want to optimize globally this functional DMN, in the case it's 0, we can do that. Why? Because we don't need to consider this Eumann space. We just consider the conformal maps. That's what we said before. When the surfaces are not isometric, so the distance is greater than 0, then the kind of situation is something like this. The conformal group is kind of disjoint from the area preserving. So what we're going to do, we're going to do a general kind of thing, which we're actually going to define in the area preserving diffeomorphism a very small set of candidates. Why do I mean small set? Because we're actually going to do something like projection of the conformal maps on the area preserving diffeomorphisms. So we get a 3-dimensional manifold inside an infinite dimensional manifold. So that's very small. And we're only going to work in that space. And what I'm going to claim to you is that in many cases we can prove that the global minimum on this group actually belong to this extremely small set. So let me actually instantiate this idea to a particular geometric functional that biologists care about and show you an algorithm and results. So, let me explain the functionals that we take. So we start from something which is well known, which is called the Procrustes distance. That's the functional. This is how they compare surfaces. You take a bunch of points on one surface, a bunch of points on another surface, defined by the user. The user marked corresponding points. Here you can see them by colors. And then the distance is defined, factor out the best rigid motion between those two sets, and take the sum of square distances. That's the Procrustes distance. Obviously, the user has a very influential role on the distance, right? He decides the points and the correspondences. So first of all, we want to get rid of the user. So what do? We replace the correspondences with continuous maps between the two surfaces. So we put here an integral on the first surface. And then we also put here the correspondence inside the search. Yeah, ignore this minimum. Let's say that we didn't prove at this point that there's a minimum. Later, maybe I'll talk about that. But anyway, there is a minimum. So we want to search both for those space of maps and the rigid motions. Now, the first question that rises is what class of transformations do we want to? 3 minutes. OK. So I'll use 2 minutes in this and 1 minute. OK, so it turns out that area-preserving diffeomorphism is the right thing. I'm not going to say more here. All I want to say is that now we have this, we call this a continuous Procrustes functional. It is defined on area-preserving diffeomorphisms. And the theorem that kind of ties this thing together says that if we have an area-preserving diffeomorphisms that gives a small Procrustes distance, then it's not far from a conformal map. Okay, so that's kind of continuity result. But why is it important? It means that if the distance is small, we can say something global about this functional over an infinite dimensional group, which is something particularly interesting because the way people kind of approach this problem is start with some initial guess that comes from another place and do gradient descent. But if for small distance and you can say something global, it means that you can do well for short distances. So the algorithm, OK, I'm not going to talk about too much. The algorithm basically takes the conformal maps, randomize the conformal map, project it on this space in a certain way, and now we just test all of them, kind of sample the conformal group, test all of them, and take the best one. Very simple algorithm. Let me answer just this thing, and I'll be done. So back to this 20 million years gap thing. So there are two groups. We got 36 models, all of them scanned by our collaborators. These are three-dimensional meshes achieved by micro-CT. These things are actually very small. And there's 3 surfaces that have been found in this special location, which means that they both from the same era, the same time in history. And these two groups are believed to be 20 millions apart. So we take this group of meshes, and we just compute the distances between all pairs. So we get a matrix of 36 by 36 with the distances between every pair. And now, in order to visualize it, I'm just going to show you kind of an embedding with relatively low distortion of those points. What you can clearly see is that the blue points is one group, the light blue points is the other group, and the three interesting ones that were found in the same place in the digging site, actually 2 of them belong pretty clearly to one group, and only 1 of them belong clearly to the other group, which might imply that these 2 groups existed together in history, and they're not really 20 millions apart. The thing I want to highlight here is it's not that this is a historical proof, but what it means is that there is some objective measure which did not involve human in any part of the process and was able to provide a representation of the data which gives a clear separation between the 2 groups. And I think that's kind of my main kind of message is that we might want to develop such algorithms that are able to provide information on our data, which is kind of more conclusive than it was originally was. I don't know if it makes sense, but that's that. OK, thank you.